We discussed in an earlier lesson how two harmonic waves meeting at a point can either constructively or destructively interfere, producing either a bigger wave or no wave at all, depending on the phase difference between the two waves when they meet. The interference of sound waves presents very interesting phenomenon, and we will spend few minutes looking at some of these phenomena. Interference of sound waves. Sound waves advancing in the same medium will generate two separate displacements on the same set of particles. For example, this is an air molecule. If there are two loudspeakers in this room, sound coming from both loudspeakers will interfere. In other words, the energy coming from both loudspeakers will produce displacements on this particle. If both displacements are in phase, the particle will have maximum displacement. In other words, you will hear a loud sound. If the two waves are out of phase, the particle will not vibrate. In other words, the sound will cancel each other. You will hear no sound. Now, this is a very interesting phenomenon. If two waves are in phase, these displacements will add up, producing a larger displacement. And in the case of sound, that means a loud sound. Now tell me, what does loudness of a sound depend on? Loudness of a sound depends on the amplitude of vibration. Now, for example, here I have a tuning fork. If I hit it very lightly, now I'm going to hit it very lightly, the energy I imparted to it is very small, means the amplitude of vibration is very small. But if I hit it a little louder, look at that. You can actually see the vibrations, large amplitude vibrations. So loudness is proportional to actually the square of the amplitude. A larger amplitude means a louder sound. So if the two waves interfere in phase, these displacements will add, producing a larger displacement, which means a louder sound. So here we have the case of two sound waves meeting in phase at a point. The compression, remember I told you, I will use the transverse wave representation to represent a sound wave, a longitudinal wave, where the crest represents a compression and the trough will represent a rarefaction. So the compression of one wave falling on the compression of another wave will produce a bigger compression. There you have a bigger amplitude and therefore a loud sound. Since the loudness of a sound is proportional to the square of the amplitude, you will hear a loud sound. If two displacements, on the other hand, are out of phase, the displacements they produce on the particle of the medium will cancel each other, and the resultant displacement will be either zero or very small, depending on the phase difference. Now, here you have the compression of one wave falling on the rarefaction of another wave. The waves are completely out of phase. The displacements are cancelled. There are no displacements. You will hear no sound. The loudness will be... Now here I have an animation. It may be difficult to figure out, but what happens is a sound advancing from the left and a sound advancing from the right superimpose one on each other. That means each particle will now be subjected to compressions and rarefactions from both waves. When compression falls on compression, you can see a region where you have a thicker shading. It shows a compression falling on a compression, producing a bigger compression, and rarefaction falling on a rarefaction, producing a bigger rarefaction. So a good example of how two sound waves interfere, producing either a loud sound or a low sound. Now, once again, the compression falling on a compression produces a large compression. A rarefaction falling on a rarefaction produces a large rarefaction. And this is what we call constructive interference. The compression of one wave falling on the rarefaction of another wave is completely destructive, producing no sound. I have another animation here. This is the case where you have two loudspeakers in a room, and if you walk from one end of the room to the other, what you will hear is actually amazing. Now, if you walk from one end to the other, there are regions where sound from each of the loudspeakers will meet in phase, producing a loud sound. And as you move further, there are regions where they will be out of phase, having no sound. So, in a situation like this, if you are very careful and listen very carefully, you can pick out places where the sound is loud and there will be no sound, loud sound, no sound, and so on. Now, in practice, it is actually difficult to get this effect done. You know why? Because when you do this experiment in a room, it is not only the direct sound coming from the loudspeakers that you hear, but also the sound reflected from the walls and the ceiling. So even at places where the two sounds from the loudspeakers cancel, you still hear the reflected sound. Also, another factor which will make it difficult is the frequencies that are produced by the two speakers have a wide range of frequencies. Now, not all frequencies will be meeting in phase and out of phase at the same time. So both these will actually make it difficult. But if you do this in a very insulated room, you can actually get that effect. Once you got two speakers producing sound of the same frequency, and if you walk from one end to the other, you can stop at a point where you hear a loud sound, then you can stop at a point where you hear no sound, and so on. A very interesting experiment. So the illustration on the right shows two speakers producing sounds of the same frequency. You see, the experiment will work only if both speakers produce the same frequency and wavelength. Now, if you walk from A to B across the room, at some points sound waves from S1 and S2 will reach you in phase, where you will hear a loud sound. And along the red lines, I have actually drawn some red lines, but that will keep changing. So you can see sounds from S1 and S2 will meet in phase along those lines. And along the green lines, they are out of phase. So as you walk from A to B, if you cut the green line, that is where you hear no sound. If you cut the red line, that is where you hear the loud sound. So you can actually pick and mark points where the sound is loud, no sound, loud sound, and so on. A very interesting experiment. Now here, this is the sound waves coming from speaker 1. and this is the sound waves coming from speaker 2. You can see here my aluminum pointer. If you can see, the compression of waves from speaker 1 falls on the compression of the waves from speaker 2. What's the result? The result is a big wave or a loud sound. So at points where this happens, you hear a loud sound. On the other hand, if the compression of the waves from speaker 1 falls on the rarefaction of the waves from speaker 2, what will happen? They will cancel each other. There will be no waves. You hear no sound. Alright. Another animation of those. Sound coming from speaker 1 and sound coming from speaker 2. If you look at this particle, look at that. This particle, now they are in phase, maximum displacement. And now they are out of phase, no displacement. You see? You can see these two waves will get in phase, out of phase. Look at that again. Maximum displacement. They are in phase now. Now they are completely out of phase. Now here you have two waves of slightly different frequency. That means they have different wavelength. As they advance from left to right, they get in phase and out of phase continuously. We will talk about this towards the end of the lesson today. Here you have now, look at this particle now. There's maximum displacement, the waves are in phase. And soon they are out of phase. And then they get in phase. And that happens continuously. And what will be the effect that you hear? When the waves are in phase, you are likely to hear a loud sound. So here you have loud sound, and now followed by no sound. Alright, loud sound now, followed by no sound. We will talk about this a little later as we move on. Let's now talk about phase difference and path difference. Phase difference and path difference. Now, you remember we talk about the phase of two particles. If one particle, tell me, if by the time one particle completes one vibration, the particle on the left completes one vibration, the energy just reaches the particle on my other hand. Now tell me, what is the phase difference between these two particles? Particle 1 has completed one vibration. The particle 2 and particle 1 are now beginning together. I can say the phase difference is 2 pi. Is that right? Because particle 1 has completed, look at this. This is 0, pi by 2, pi, 3 pi by 2, 2 pi, and now the two particles are beginning. A phase difference of 2 pi. What is the distance between these two particles now? The distance between nearest particles that are in phase is a wavelength. That means a phase difference of 2 pi equal to a distance of 1 wavelength. Did you understand that? Let me see if I can show that over here. If there are two particles, one here and one here, this one has completed one vibration. That means it has gone through a phase of 2 pi, and this is the second particle is now beginning to vibrate. Therefore, we say the phase difference between the two particles is 2 pi. Now, the phase difference between these two particles is 2 pi, means this has completed one vibration when this just begins. That means they are in the same phase of vibration. A phase difference of 2 pi actually means in the same phase. Now, what is the distance between these two particles? Is 1 wavelength. So, the distance here is 1 wavelength. So, 1 wavelength, a difference of 1 wavelength is equivalent to a phase difference of 2 pi. That means a distance of lambda by 2 is equivalent to a phase difference of pi. A distance of a quarter lambda is equivalent to a phase difference of pi by 2, and so on. When the distance between the two particles is a wavelength, the phase difference is 2 pi. If the distance between the particles is half a wavelength, here there's a particle here, the phase difference between those two particles will be pi. They will be completely out of phase. If the distance between the two particles is a quarter of a lambda, the phase difference will be pi by 2. I want you to remember the relationship between the wavelength and phase difference. We will be using that as we go on in the next couple of slides. Okay. Now, if one wave starts from point A and another of the same frequency starts from point B, how do we know if they are in phase or out of phase when they meet at point C? Can you tell me, is there any way that you can tell if the waves from A, suppose this is loudspeaker 1, B is loudspeaker 2. Both the waves from speaker 1 and speaker 2 reach point C. Is there any way to tell whether those waves are in phase and out of phase? Alright? When a wave propagates in the medium, particles of the medium in intervals of 1 wavelength are in the same phase of vibration. That's what I was showing you a little earlier. Particles that are in intervals of 1 wavelength are in the same phase of vibration. How about particles in an interval of 2 wavelengths? They will also be in the same phase. How about particles in intervals of 5 wavelengths? They will also be in the same phase. For example, now, if these are 2 particles, the distance between them is 1 wavelength, they will be in phase. If the distance between 2 particles is 5 wavelengths, they will be again in phase. Alright? If there are 50 whole waves in the distance from A to C, and 44 whole waves in the distance from B to C. I'm just giving you some numbers. Suppose there are 50 whole waves in the distance from A to C and 44 whole waves in the distance from B to C. Tell me, will those waves meeting at C, will they be in phase or out of phase? Well, they will be in phase because all whole number difference in wavelength will be in phase. In other words, if there are 100 waves in the distance AC and 200 waves in the distance BC, the difference between the two is 100 whole waves. That means they will be meeting in phase. So, if the difference between the paths taken by the 2 waves to reach C differs by an integer multiple of the wavelength. For example, if the difference between the path AC and BC contains an integer multiple of the wavelength, 1 lambda, 2 lambda, 3 lambda, 5 lambda, 50 lambda, and so on, then they will meet in phase at C. Now, what is the meaning of path to difference? Path to difference is the difference between the length of the path. So, if the path to difference between AC and BC is an integer multiple of a wavelength, then the waves from A and B will reach C in phase. You will hear a loud sound. So for any integer n, the condition for two waves to meet in phase, what is the condition? That their path to difference must be equal to n lambda, where n is an integer. N can be any integer, 1, 2, 3, 4, 5, and so on. So one more time, if the path to difference between waves from A and B reaching C is an integer multiple of a wavelength, then the waves from A and B will reach C in phase. On the other hand, what is the condition that they will be meeting out of phase, or they will destroy each other? The condition for destructive interference happens when the path difference is an odd multiple of half a wavelength. Remember, I just showed you, if the distance between two particles is half of a wavelength, they will be completely out of phase. So, if the waves coming from A and the waves coming from B, when they reach at C, if the difference between the path they take differs by an odd multiple of half a wavelength. Why do we have to have odd multiple of half a wavelength? Because when you take even multiple of half a wavelength, they will become integer numbers. Now what we need for destructive interference is that the path to difference must be some odd multiple of half a wavelength. 1 lambda by 2, 3 lambda by 2, 5 lambda by 2, and so on. If the path to difference is an odd multiple of half a wavelength, then the waves from A and B will reach C completely out of phase. And so, we will say the condition for destructive interference is the path to difference must be 2n plus 1 lambda by 2. 2n plus 1, where n is an integer, 2n plus 1 is always odd. When n equal to 0, this will be 1. When n equal to 2, 2n plus 1 is 5. When n equal to 4, 2n plus 1 is 9. So, if n is an integer, 2n plus 1 will always be odd. The condition for destructive interference is, what is the condition? That the path to difference must be equal to, an odd integer multiple of half a wavelength. That is the condition for destructive interference. For constructive interference, the path to difference must be equal to an integer multiple of the wavelength. For destructive interference, the path to difference must be an odd integer multiple of half a wavelength. Alright? Let's, you know that the path to difference of lambda is equivalent to a phase difference of 2 pi. If there are 6 whole waves in the distance AC and 6.5 waves in the distance BC, then the path to difference will be half a wavelength when they reach C. That means waves from A and waves from B will reach C completely out of phase, and there will be no sound at that time. That means a phase difference of pi is the same as a path difference of lambda by 2. A phase difference of pi by 2 is the same as a path difference of lambda by 4. I wrote down this for you in the beginning earlier on. Let's do an example. Two sounds of the same frequency, 170 Hertz, are produced at points A and B, and these waves are detected at point C. You need to find what are the path difference and the corresponding phase difference for waves reaching C if C is 10 meters from A and 14 meters from B. Well, there are three situations. Let's take one at a time. Alright, in case 1, distance AC is 10 meters and distance BC is 14 meters. And what are the things that we know in this problem? The frequency of the sounds, both frequencies are the same, and that is 170 Hertz. The amplitude of vibration is 0.025 meter. Well, I haven't given it to you here. Well, I meant to give it to you. That is the amplitude. The velocity, the speed of sound in air is 340 meters per second. I don't have to give it to you. You're supposed to know that. Alright, first we find the wavelength, the lambda, of the waves that are produced. Now, how do you find the wavelength? You know the frequency, you know the wave speed. Therefore, wavelength lambda equal to V over F. That will be 340 meters per second divided by 170 per second. That is 2 meters. The wavelength of the waves starting from A and B is 2 meters. Alright, once you know that, we can now take part A. In part A, distance AC is 10 meters and distance BC is 14 meters. Tell me, what is the path difference between waves from A and B reaching at C? The path difference is 14 meters minus 10 meters, which is 4 meters. Well, this 4 meters is equal to 2 full wavelengths because one wavelength is 2 meters. Alright? If the path difference between the waves starting from A and B is 2 full wavelengths, tell me, are the waves arriving at C in phase or out of phase? They are arriving in phase. That means the amplitude of vibration there will be twice the amplitude. The amplitude will be 2 times this value. So as the path difference is an integer multiple of a wavelength, these waves are in phase. That means the phase difference is 0. Alright. In B part, the distance AC is 10 meters and the distance BC is 11 meters. What is the path difference? The path difference between AC and BC is 11 meters minus 10 meters, that is 1 meter. If it is 1 meter, what part of a wavelength is it? The wavelength is 2 meters, therefore this path difference of 1 meter is half of a wavelength. Alright? If the path difference is half of a wavelength, what is the corresponding phase difference? Yes? A path difference of half a wavelength is equivalent to a phase difference of pi. So these waves are completely out of phase. The phase difference is pi. That means the resultant displacement at C will be 0. You will hear no sound at C. Alright, let's do now the C part. Distance from A to C, distance AC is 10 meter. Distance BC is 10.5 meter. What is the path difference this time? The path difference between AC and BC is 10.5 meter minus 10 meter, that is 0.5 of a meter. Tell me, what part of a wavelength is this 0.5 meter? A wavelength is 2 meter. Therefore, this path difference of 0.5 meter equal to a quarter of a wavelength. Now, what is the corresponding phase difference? The corresponding phase difference is pi by 2. Therefore, the amplitude when they meet at that point will be, well, will be 2a cos delta by 2, right? 2a cos delta by 2. Delta is pi by 2. And delta by 2 will be pi by 4. So the resultant amplitude will be 2a cos pi by 4. You can work it out on your own. There will be some sound there. It will not be a maximum. It will not be a minimum. It will be somewhere in between. Another problem. Two sound waves oscillate in phase with a frequency of 100 Hertz. At a 0.5 meter from one source and 5.85 meter from the other source, the amplitude from each source separately is A. What is the phase difference between the waves from these two sources at that point? Well, what are the given data? The frequency of the sound produced by both sources is 100 Hertz, and you know the speed of sound is 340 meters per second. That means we can calculate the wavelength. Once you have the frequency and the speed of the wave, we can calculate the wavelength. Wavelength lambda is V over F. That will be 340 meters per second divided by 100 per second, which is 3.4 meter. Okay, now tell me, the point at a 0.5 meter from one source and 5.8 meter from the other source, what is the path difference between the paths taken by these two waves? The path difference of the point from the two sources is 5.85 minus 5, that is 0.85 meter. Can you tell me, this 0.85 meter is what part of this wavelength? Well, that is a quarter of a wavelength, because 0.85 is a quarter of 3.4. So the path difference between the 2 points for the waves reaching at that point is lambda by 4. What is the corresponding phase difference? A path difference of a quarter lambda corresponds to a phase difference of pi by 2. Yes? So the phase difference therefore is pi by 2. So you must be able to do these kind of problems. If you know the path difference, you must be able to find the phase difference. What is the amplitude of the resultant wave? The same problem. What is the amplitude of the resultant wave? Well, if delta equal to pi by 2, A prime is the amplitude of the waves meeting at that point. Do you remember the equation for the amplitude? The amplitude, the resultant amplitude is 2a cos delta by 2. I hope you remember from our discussion from harmonic waves earlier. So if A prime is the amplitude when the two waves meet at that point, that A prime will be 2a cos delta by 2. Now, delta by 2, delta is pi by 2, therefore delta by 2 will be pi by 4. It will be 2a cos pi by 4. Anybody tell me the value of cos pi by 4? It is square root 2 over 2. So if this is square root 2 over 2, the 2 on the denominator will cancel with this 2. So the answer is square root 2 times a, where a is the amplitude of each wave that is arriving at C. Alright? Okay, that's one of the problems. Two loudspeakers are separated by a distance of 6 meters. A listener sits directly in front of one speaker at a distance of 8 meters, so that the two speakers and the listener form a right triangle. Find the lowest frequencies for which the path difference from the two speakers to the listener will be an odd 1/2 multiple of the wavelength. Well, if the path difference is an odd multiple of 1/2 of the wavelength, then the two waves will be arriving out of phase. There will be no sound at that point. Alright, what are the given situations? This is the given situation. Two loudspeakers, these are the two loudspeakers, and here is the listener listening the two sounds coming from the speakers. Now the listener is 8 meters from one speaker, that is, this is 8 meters, and the two speakers are 6 meters apart. That means the distance of the listener from the second speaker is this. That is the hypotenuse of this right triangle. If this distance is 6, this is 8, then that hypotenuse is 10 meters. Alright? So once you figure out the diagram, we can now start the problem. What is the path difference between the waves from speaker 1 and speaker 2 reaching the listener? The path difference will be 10 meters. The waves from speaker 2 will travel 10 meters. The waves from speaker 1 will travel 8 meters. The path difference is 2 meters. Alright? When the path difference is an odd multiple of lambda by 2. Now, we are told that we need to find the condition. What are we supposed to find? Find the lowest frequencies for which the path difference, this path difference, which is 2 meters, will be an odd multiple of half a wavelength. Now, how do you write odd multiple of half a wavelength? 2n plus 1 times lambda by 2. This is how you represent the odd integer multiple of half a wavelength. And the path difference that is 2 meters must be equal to an odd multiple of half a wavelength. So we have the equation 2n plus 1 times lambda by 2 must be equal to the path difference 2. And we need to find the lowest frequencies. That means the lowest frequencies will correspond to the lowest values of n. What are the lowest values of n? Integer values. N equal to 0 and 1 are the two lowest values. Alright? Two lowest frequencies correspond to n equal to 0 and n equal to 1. So what we will do is, we will assign n equal to 0 here and find the corresponding value of the wavelength. Once you know the wavelength, we can then figure out the frequency. You see that? So, when n equal to 0, what do you have? 2n will be 0, 2n plus 1 will be 1. The left hand side will be simply lambda by 2. Lambda by 2 will be equal to 2, or lambda will be equal to 4 meter. So the lowest frequency that will arrive at that point, completely out of phase, will have a wavelength of 4 meter. Now, if the wavelength is 4 meter, what's the frequency? Frequency equal to V over lambda. V is 340 meter per second, divided by lambda is 4 meter. That is 85 hertz. That is the lowest frequency that will arrive completely out of phase. What is the next higher frequency that will be out of phase? That will correspond to n equal to 1. When n equal to 1, 2n plus 1 will be 3. 3 lambda by 2 equal to 4. 3 lambda by 2 equal to 2, or 3 lambda equal to 4, lambda equal to 4 over 3 meter. If lambda is 4 over 3 meter, what is the frequency? Frequency is 340, that is the velocity, divided by the wavelength is 4 over 3 meter. What is that equal to? That will be 255 hertz. So these are the two lowest frequencies for which the path difference will be an odd multiple of half a wavelength. I hope you understood the way I argued this problem out. Okay. Next part of the same problem. Why can these frequencies be heard even if the speakers are driven by the same amplifier? You see, in practice, you still be able to hear these frequencies, although these frequencies arrive at the listener completely out of phase. But the reason why you can hear them is that the sound you hear are not only the direct sound from the speakers, but also the reflected sound from the walls and the ceilings, and that's why you can still hear it. The waves coming towards the listener directly from the speakers undergo destructive interference at these frequencies, but they also get reflected from various parts of the room and reach the listener, enabling the listener to listen to the frequencies. Let's now talk about a very interesting phenomenon called beats. In fact, that is what I had actually demonstrated to you earlier. What is beats? Beats. Well, the figure shows two sound waves advancing in the same direction. What is the characteristics of these two sound waves? These two sound waves, one has a frequency of 10 hertz, the other has a frequency of 12 hertz. That means they are very nearly equal frequency, but not exactly the same. That means they have slightly different wavelength. Now, if you notice, they are starting out in phase, but as they advance, they go completely out of phase. Can you see here? Red wave and blue wave, they are completely out of phase. Compression of one falls on the rarefaction of the other. But as they advance, they soon come in phase. Here the compression falls on compression and rarefaction falls on rarefaction. They are in phase. And very soon they get out of phase. Here they are completely out of phase. And now they are in phase again. Why does this happen? Because they have slightly different wavelength. So, when two sound waves of very nearly equal frequency are sounded together, what will happen? As they advance, they get in phase, out of phase, in phase, out of phase, in phase, continuously. And what do you hear as a result of that? When they are in phase, you hear a loud sound. When they are out of phase, you hear no sound. Again, you will hear this intermittent loud sound, no sound, loud sound, no sound. And this is what we call beats. They have the same amplitude, but they differ slightly in frequency, and therefore they differ slightly in wavelength. If they start out together from a point, they will be in phase when they start out, and therefore you get a very loud sound. But soon as they advance, they gradually get out of phase. You see, if this is where they are in phase, you can see this is where they are in phase, you get a loud sound. But soon they get out of phase, they cancel each other, producing no sound. At some point they will be completely out of phase, and there you have no sound at all. And again, as they advance, they get in phase. That means you got a bigger amplitude, therefore you have a loud sound. Isn't that interesting? Now, do you think you can produce that effect in actual practice? Well, this is the animation I showed you earlier. The wave above and the wave below. There are two waves advancing in the same direction, and they differ slightly in wavelength. That means as they advance, just watch just one particle. As they advance, they get in phase, look at that. Out of phase, in phase, loud sound, no sound, now loud sound, no sound, and so on. This beautiful process is what we call beats. So this phenomenon is what we call beats. And you hear the waxing and waning of sound. Loud sound, no sound, loud sound, no sound. So this waxing and waning of the sound as two sound waves advance in the same direction is actually called beats. Now, what is the prerequisite for producing beats? The frequency difference should not be too much. The frequency difference must be very small. If the difference between the frequency is very large, there will be too many beats which will sound continuous. Now, let's see if I can demonstrate that for you. Now here, I'm going to, now this is one tuning fork. I'm going to vibrate this one. I'm going to see if you can actually see this. Alright, let me see if I can show that to you. Now here I have two tuning forks. One is this. I'm going to keep it on a base here. And the other is this. I'm going to sound each and listen to the sound. That's the first one. That second one. They are very nearly equal frequency. Alright, I'm going to now sound them together. You've got to listen carefully how they sound. Alright, the first one. Do you really hear that waxing and waning of the loud sound and no sound? Try it one more time. Alright, let me change the frequency slightly and see if it makes any difference. Now, is the beat frequency great? What's the meaning of beat frequency? Beat frequency is the number of highs and lows you hear. And that is actually equal to the difference between the frequencies. Now, look at, listen to this. Can you hear the beats? Alright, I'm going to change the frequency. You tell me, is the beat frequency greater or smaller? There are more beats now. Alright, listen to this one more time. Well, the beat frequency is decreased. That means the frequencies are coming closer together. Now, just one more time and see if you can pick it up. Just one more. Do you hear that? Well, I want to do it one more time. There you are. The frequencies are coming very close to each other. Beats is a beautiful phenomenon in interference of sound. Is that right? Okay. Now let's have a look at a computer animation of beats. I have a 437 Hertz and 437 Hertz. If I sound them together, will there be beats? Let's sound them together and see what sounds like. 437, 437. There are no beats. Let's have 437 and 438. Now, beat frequency here, the difference between the frequency is 1 Hertz. That means there will be 1 beat per second. The beat frequency is the difference between the frequency. Let's look at the difference. Now, another difference, 437 and 442. There is the difference of 5 Hertz. And listen to that. That is 5 beats per second. You can actually play with it. 443, there will be 6 beats per second. Alright, so we have actually experienced. Let's now look at a couple of problems. 2 tuning forks have frequencies of 256 and 260 Hertz. If the forks are vibrating at the same time, what is the beat frequency? Well, I don't think you need my help to do that problem. The beat frequency will be the difference between the 2 frequencies. So the beat frequency here is 4. Alright, let's look at another problem. When a violin string is played without fingering, simultaneously with a tuning fork of frequency 480 Hertz, beats are heard at the rate of 4 per second. 4 beats are heard per second. It means the frequency of the violin string is either 4 greater than 480 or 4 less. The beat frequency only tell you that there is a difference of 4 Hertz between the frequencies. When the tension in the string is increased slightly, you know how to increase the tension on a string? By tightening it. You know, this is how you tune the violin or guitar wire. You can use a tuning fork and listen to the beats and change the tension until the beat disappears. then the two frequencies will be exactly the same. So when the tension in the string is increased, means the frequency is increased. The beat frequency decreases. That means the frequencies come closer to each other. What was the initial frequency of the violin string? Alright, the beat frequency is 4, means that the difference between the frequency of the tuning fork and the frequency of the violin string is 4. So that tells me that the frequency of the violin string is either 4 less than 480, that is 476, or 484. Now we got to decide which is the actual frequency of the violin string before tuning. Now what happened? When the tension in the string is increased, means the frequency of the violin string is increased, the beat frequency decreases. So can you tell me which of these is therefore the actual frequency of the string before tuning? Well, this is the frequency of the tuning fork, 480. That means the frequency of the violin string can be either 476 or 484. And now what happened? When the tension on the string is increased, the frequency of the string also increases. And what happened? When the frequency of the string is increased, the beat frequency decreases. Now, if the frequency of the string were 484 to begin with, if you increase the frequency, that means it is going to go to 485, 486 and so on, which means the beat frequency must increase. Is that right? But the beat frequency decreased, which means the frequency of the violin string is now approaching the frequency of the tuning fork. That means this must be the original value and not this one. This is how you argue out to solve the problem. So the frequency of the violin string is approaching 480. Therefore, the higher of the frequency belongs to the tuning fork. If the violin has to approach the frequency of the tuning fork when its frequency is increased, that means the higher frequency must be that of the tuning fork and the lower frequency must be that of the violin string. So what's the answer? The answer is 476 Hertz. Well, this has been a very useful and interesting lesson, and there is another part of this lesson, 1.5a, that is called resonance. Another very interesting aspect of sound waves, and that I will do later for you. Alright? In the meantime, look through this and see whether you need any help. Alright, let me know. I will get back to you with the next part of the lesson a little later.